Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, this opportunity we have just to meet and study your creation. I just pray that you'd, again, be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So, so that quiz, a couple of the problems I have given on a test before, so here those are. So like this is problem 1 on your quiz. So basically you just calculate the divergence, and when you do that you should see what you get is x squared. So x of course is equal to rho squared cosine squared theta sine squared phi. And then I guess pretty obviously you want to use spherical coordinates here, right? I mean, definitely. This is obviously a spherical coordinate problem, so we trade our x squared for its spherical equivalent. My dv is rho squared sine phi d rho d phi d theta as usual. We integrate over the full range of colatitude and theta, and 0 to r for my rho. And so you're up against integral of cosine squared and an integral of sine cubed, but we know how to do those. So we do, and out pops 4 pi r to the 5th over 15. So once you have everything understood, once you're done studying for this course, this should not be a difficult problem. This should be a moderate to / easy problem for this part of the course. Everybody here ought to be able to do this problem in like 10 minutes max, like comfortably in 10 minutes. All right? If you don't know the integral of cosine squared and sine cubed at this point in the course, you need to stop what you're doing and go learn it. These matter, all right? You also have like a note card. So if for some reason you've got some kind of like integral of sine cubed or integral of cosine squared phobia, you can record the answer on the note card. But I don't think you have that. I think you just, every time you come to it, you're like, oh, I forgot how to do that. And then you look it up somewhere, write the answer down, and then proceed not to learn it, right? Because you're just looking it up and copying it down rather than learning it. But anyway, that's my theory. I'm sticking to it. Now here's a worse picture of what I have. I think I did better this morning. Oops. Interesting. Anyway, I hadn't thought about using this to get stuff off the ceiling. Guess you could, if it's close enough to the board. Anyway, okay. Anyway, so here's a horrible picture of this plane. It's a subset of the plane containing these 4 points, right? And again, the shadow of these onto the xy plane is just the unit square. The normal to the plane is -1, 0, -1, 1. That points upward, yay. And the equation of it is y minus z equals to 0. So we just put x, y, y. That's my parameterization. I work out my, my surface area element is this. My curl for this vector field is just 0, 1, 0. So when we do Stokes' theorem, the integral around the boundary of the square is equal to the integral of the flux, surface integral of the flux on the square, which is just equal to this, which is -1. So again, once you have everything in order, this should not be a difficult problem. Right? This is like now, I don't think this is as easy as the first one by any stretch of the imagination. I mean, the integration here is easier, right? Once you get through it. But now I don't have the third problem solved, so sorry about that. What do you think? How do we think you solve the third problem, though? What's the idea of the third problem?
Solve it for the whole box and then subtract the top.
Yeah, solve it for the whole box and then subtract the top is the right idea. So basically, you're trying to find the flux through, all these faces, right? And this is empty up here. So you just calculate the flux from the whole box, which you can do by the divergence theorem pretty easy, right? And then calculate the flux of the top face directly. That's actually pretty easy because I made the formula work out so that the vector field's constant on the top face. And then you just subtract the flux from the top face from the flux of the whole box, and that gives you the flux on the surface S, which is given. So yeah, that's the idea there. So any questions, guys, about homework or anything? All right, well, let me talk a little bit more about physics then. Example 1 here. Oh, goodness gracious, if I can remember, this is a question, is can I actually remember it? Yowzers. Oh, I found this example earlier, now I've lost it. See, I need to teach physics 2 again, because I'm starting to forget these formulas, which is for shame. Shame, shame, shame on me. But there's a law called Faraday's law, and I'm not quite sure up to a sign what it was. I've got it written in the notes somewhere here. Let me see if I can find it again. Oh, there it is. The curl of the electric field is equal to minus the time rate of change of the magnetic field. All right? So I just want to talk about what Stokes' theorem has to say about this. This actually is going to combine a few different concepts for us. So one of the concepts I should mention is that you can define the voltage. All right, the voltage at say R is defined by minus the integral from the potential to R of the electric field dotted dr. And this makes sense because the electric field's path independent. That defines the voltage function. If you write this down, what does this make the gradient? What's electric field then? Electric field is equal to minus the gradient of the voltage function. Okay? So that's how you define voltage from the line integral of the electric field. Do you guys remember that from your high school physics? You really shouldn't. For one reason, you didn't have high school physics, as I was just told. But even if you had a high school physics which meaningfully implemented Calculus 3 in the theory of the course, well, you had a high school professor who was really misbehaving. Hats off to that person. But unless you went to like a governor's school or like the, like the fancy schmancy elite high school of the state that you were in, probably you didn't see that, right? Anyway, so that's how we could define voltage from the line integral of the electric field, like that. So I can study what this differential. So this is called Faraday's law. This doesn't look like the Faraday's law that you'll see in physics 2. Not at first glance anyway, because there we present it in an integral form. Let's see here. So what I need to do is I need to think about like a surface. All right. Let's say like this surface. And so of course this would be like the boundary of the surface would be like that. So I guess I'm supposing that the the normal's like so. All right. But let's try to integrate Faraday's law in differential form and see if we can understand what its integral form is, which for those of you who take Physics 232, you'll see it again there. All right, so here we go. We calculate the surface integral of the curl of the electric field, right, around the boundary. Oh, my bad. Come on, good grief. What's wrong with me? We calculate the surface integral of the curl. So surface integral, do I put a dr here? No. Surface integral, so ds vector, right? It's not around the boundary, it's on the surface. So surface integrals are for surface. Line integrals are for curves or lines. So according to Stokes' theorem, this is equal to the integral around the boundary, right? Around the boundary of the surface of the electric field. So the circulation of the electric field around the boundary. So guys, the voltage, right? If you calculate the difference in the voltage going from one point to another, you get the change in the voltage, right? So here, what are we doing? We're integrating the electric field all the way around the loop, right? So what this is equal to, you know, well, I need a symbol for it. We usually use this, like E, the voltage in the loop, right? So that's the voltage around the loop. If you were to imagine sticking a little resistor in here like this, resistor, that would be the voltage dropped across that resistor. All right. But on the other hand, what's this equal to? According to Faraday's law, this is equal to the integral of this over the surface of minus the time rate change of the magnetic field dot ds, right? And then the thing is, if the loop is not changing in size, all right, suppose that the loop itself is not dynamic, all right? The surface in question is a real physical surface and it's not changing in size. Like S is fixed in time. If that's the case, then it's reasonable to pull the time derivative out of the integral. And so what you'd have is minus partial t of the integral over the surface of B dot ds in that context. But what is that? What is the integral of B dot ds over the surface? Well, that's the flux of the magnetic field. All right, so what you've got here then is basically minus the rate of change of the magnetic flux per unit time. And so that's Faraday's law. Faraday's law says that the voltage induced in a loop is proportional. It's proportional to the rate of change of the magnetic flux through the loop. This is Faraday's law, which says that when you change the magnetic flux, the number of field lines going through a loop, it induces a voltage around the loop. And the rule for it is that the current has to be induced in such a way to maintain the magnetic field in the way it was before it was changing. So the induced current attempts to oppose a change in flux through the loop. This is Faraday's law. So, yep. Anyway. One of the other things I should tell you guys about before I forget. Well, actually, let me wrap up this physics discussion here, and then I'll get back to the other thing, okay? So the physics discussion is really, in my notes, there's this section on potential theory. And I don't think I really have much in the way of homework for you, so this is kind of an optional section, which I sometimes get to and I sometimes don't. And you know, you guys have been a good class this semester, so I'll spend a couple minutes of class time on it at least. Once upon a time, I spent a week on this material, and you know, but I don't think you guys are where you need to be for me to do that. So I'm just going to go over it more lightly here for you guys. And if it's okay with you, I'm going to let you not come in Friday. Is that okay? You're like, we still have to go to Sprano's class. What does it matter? Am I right? No? No? All right. So but let me finish the material. All right. So in my notes at least. I won't go over the proofs, but I want to explain to you the content of what this is saying, all right? Because basically what I'm inviting you to do is later, once you've taken Physics 2, if you're such a person, come back to these notes, study them again at that point, and try to understand them for yourself, what they're saying, because, where's my laser? Really? You know, so annoying. Because the theory that I present here, these are the next step past Green-Stokes and divergence theorem. So these are Green's identities and Helmholtz's theorem. And so here's Green's identities. In particular, if you have the dot product of two gradients plus the volume integral of f times the Laplacian of g, well, you can trade it for the surface integral of f del g over the surface. These are actually pretty fun to derive. These make decent homework problems. We could derive this in class in about 5 minutes. It's a decent thing to try for yourself. There's simple consequences of like the divergence theorem, I believe. I mean, it's a link between a triple integral and a surface integral, right? So this is going to be a derived consequence of the divergence theorem. And probably likewise down here, the symmetric, so the difference of these two guys is equal to that. Great. These are Green's first and second identities. So that's those are kind of neat. I have assigned, and I may well have assigned some of those as homework to you right now. I forgot if I have or haven't. If I have, great, you'll enjoy them. They're not bad. If I haven't, I'm sorry. Maybe I'll put it on the math battle. Anyway, so, and the reason I might put it on the math battle, again, is that these are just simple consequences, logical consequences of the divergence theorem. They're not physics, okay? Okay. And once you know these, you can derive these. A harmonic function, what's a harmonic function? A harmonic function is a function which solves Laplace's equation. This nabla squared f, what that is partial x squared plus partial y squared plus partial z squared acting on f. It's like the second partial derivatives added together set equal to 0. This is Laplace's equation. And so if you have a solution to Laplace's equation, you can say really cool stuff about it. For one thing, the flux of the gradient of a function like that is 0 through the boundary of such a surface, such a volume rather. And also the triple integral of the dot product of the gradient is equal to the integral over the boundary of this, which is interesting because this tells you about the magnitude of the gradient, right? This is the magnitude of the gradient squared. It says that the magnitude of the gradient squared, the integral of that over the volume, is somehow related to the values of the gradient, the flux of the gradient through the surface, the edge of the volume. That's interesting. And also, if you have it's 0, if you have a function is harmonic and it's 0 on the boundary, that implies it's identically 0 throughout the totality of the volume bounded. That's a pretty neat theorem. It says 0 on the edge means 0 throughout if it's harmonic. That's an interesting result. And finally, this here, nabla squared v1 equal to b, nabla squared v2 equal to b. And if they're equal on the boundary, well then they're equal throughout. Let me explain to you what this means. So this actually is the kind of equation that you get for the voltage. You see, because, see this right here? If we take the divergence of that, we get minus the divergence of the gradient of v. This is what is denoted by, this is actually minus nabla squared v. And remember, I don't know if you remember or not, but as we talked about last class, the divergence of the electric field is the charge density divided by epsilon naught. So this right here is an equation exactly of that form. It's exactly of this form. I mean, I got the minus on the wrong side, but you understand. I can move the minus to the other side. This is what's known as Poisson's equation. And so what, I can't spell it. Anyway, you'll figure it out. Poisson's equation, what this item 4 says is that if you have a solution for the voltage on some volume, right? In other words, a solution to Poisson's equation, then there is a unique voltage function which does that if you're given a set of boundary conditions on the edge. So anyway, this is physically relevant. It basically says our concept of voltage is well defined. Now, that brings you to Green's third identity. Green's third identity is, yeah. So if you have a twice differentiable function and you introduce derivatives with respect to the prime variables like so, you can build this identity for the function. It's equal to the triple integral of the Laplacian, an integral of the Laplacian divided by this distance between between the point and the prime point, integrated over the prime point. And then also this other term, which involves the gradient of the reciprocal function and this business over here. It takes about 2 pages to prove that. I have proved it in Calc 3 before. It can be done. It's not that hard, actually. It's just one step at a time. And here they are. Here are all those steps. All this math does, essentially, is deal with the divergence at the origin that we faced with our Coulomb field discussion. It's essentially getting behind that, under the hood of it, if you will. So anyway, you can prove that. And then if you know that, if you're looking at trying to solve this equation, nabla squared f equals to b, you can use Green's third identity. And if you go back to that ugly formula, you can see that the second terms in it are automatically 0, and you're just left with the first term, which means you got this formula. You can solve this, you can solve Poisson's equation in particular by just integrating the triple integral of the Laplacian divided by that dv. In other words, you get straight up a solution. I mean, this is a solution. Sorry, I've lost my place. Let h equal to this. Right. So this allows us to solve Poisson's equation through integration. Here it is specifically. This is the integral solution to Poisson's equation. If you're trying to solve nabla squared f equal to b for some continuous function b on a simple solid region E, you just integrate b divided by 4 pi divided by the distance between the point you're trying to find the solution at and the integration variable r prime. So like if you were to put this into practice for the physical problem of Poisson's equation, what would you be integrating? Well, let me zoom out a bit here. So if you look at that, over here, if I do this for this one, what's the specific solution I have? I've got the voltage at position R is equal to what? There's a minus, that minus compensates, and we're just left with like the triple 1 over 4 pi epsilon naught triple integral of the density at r prime dv prime divided by the difference between r and r prime. Now that might not look familiar to you, but this is exactly what we write down for the formula to calculate the voltage for a charge distribution in physics 232. And what this is, like, basically what we do in physics 232 is we say, well, the little bit of voltage that you get from a little bit of point charge is like essentially dq over 4 pi epsilon naught, and we might use like script r. So this would be like script r. It's the distance between r and r prime, like that. So that's the little bit of voltage from a point charge dq, and if you just add those all up, you get the total voltage. So that's what this integral is. And then like next up, there's Helmholtz's theorem. Helmholtz's theorem says if you've got a vector field, you can actually write it as a sum of a piece which is conservative and a piece which is a curl, given certain conditions which I have certainly forgotten. But this is kind of a wild theorem, right? If you've got a vector field, I guess I do need to have the divergence is that and the curl is that. If that's the case, what else do I need? I need the f goes to 0 as it has to be like a bounded vector field. So if you go really far out, the components of the vector field are going to 0. That much I need. Okay. But if I have that condition, and if it happens faster than the reciprocal of the distance squared, then you can find unique vector fields unique function u and vector field w. I guess they're probably not unique. Oh, they are unique because why? As my little brother used to say, Cosby, why? But anyway. No, the reason that these are unique is there's formulas right here. Here's the formulas. Okay, so, yeah. So you can calculate the potential for it by integrating the d term, the divergence of your vector field, right? That is essentially what I just wrote down over here in the case of the electric field, since its divergence is minus rho over epsilon naught, and the curl of the electric field, on the other hand, is 0. Well, the curl of the electric field, is the curl of the electric field 0? Not generally. Right? The curl of the electric field is generally based on the time rate change of the magnetic field, but in the electrostatic situation, the curl of the electric field is 0. Anyway, so you can find this w over here according to the integral of the curl divided by the distance. Right? Yep.
Could you use that to construct a function with a specific curl and divergence? So like you start with the curl and divergence and put them together.
Your question is, could you use this theorem to construct a vector field that has a desired curl and divergence? Yes. Yes, you could. That's right. This allows us to reverse engineer a vector field to have a designer D and C for the divergence and the curl respectively. That's what it does. Yeah. This is not usually taught in Calculus 3, all right? I'm sharing with you guys something that you're maybe not supposed to know. These particular section of my notes is taken from Susan Cully's so-called vector calculus book, which is an honest-to-goodness good Calculus 3 book, in that it's a book that is just about Calculus 3. Unfortunately, most of the mainline calculus books, they've got Calculus 1 and Calculus 2. By the time they get to Calculus 3, it's kind of an afterthought, you know? It really is. So anyway, so here's Maxwell's equations again. And so basically, now that Sam's question is really good because Maxwell's equations basically specify divergence and curl for the electric and magnetic field. The theorem which I just had up there tells you how to build the electric and magnetic field through integration. But that's exactly the theory of potentials. Like the D, well anyway, let me get to it here. So I talked about that last class. I talked about that last class. I talked about that last class. I even talked about that last class. Faraday's law we just did. The divergence of the magnetic field is 0. If the divergence of the magnetic field was not 0, there'd be something called magnetic charge. All right? If there was such a thing as magnetic charge, it would be different than what we observe in nature. We've been looking for a magnetic monopole for I don't know, a century now, something like that. The interesting thing is, there are quantum mechanical arguments. If there exists one magnetic monopole, there is a relatively simple argument in quantum mechanics which says that the charge, like electric charge, has to be quantized. It has to come in integer multiples of some basic unit of charge. That is experimentally observed. It's been known since Thomas's oil drop experiment that basically observed charge comes in multiples of the electron charge, 1.602 times 10 to the minus 19th coulombs, which is a number which I don't know why I remember. But anyway, if there was even one magnetic monopole, then that would give us a derivation that charge is quantized, which it is. So that's why people are like, well, there's got to be a magnetic monopole out there somewhere because charge is quantized, right? But no one has found it so far. It's like a big open problem in physics. Fun fact, if you can find really old physics books, from, I don't know, maybe 1920 to 1940, something like that, they actually had basic introductory physics problems on monopoles. there was a time when those kinds of problems were included in like the freshman physics kind of book. But then at some point, the physics community started being, all right, well, this is kind of make-believe, so we got to take it out of the basic physics book, right? Which is kind of funny. So in physics, if you're talking about electric and magnetic fields, you can derive them from, oh, there's a vector missing here. That's supposed to be vector A. Sorry about that. So the electric and the magnetic field can be derived from the voltage function and this A, which is called the vector potential. The vector potential is something you will not see in Physics 232. That would be taught in the junior level class in electromagnetism, which we don't currently offer residentially, but hopefully someday soon. That's a course I'd like to teach, but not sure I really have the, I only have a master's in physics. Maybe I shouldn't teach that class, right? But it turns out that these formulas, if you have electric field as the gradient of phi and plus the time derivative of the vector potential, and like this for B, then you can derive the electric and magnetic fields to satisfy Maxwell's equations, provided that you construct the voltage and the, so basically this phi is like the, let's see, it's like the, goodness gracious, I'm trying to think. Well, anyway. The interesting thing is with the voltage is, like it's not, there's not a unique choice. The potentials are not, the magnetic field and the electric field, those are like physical, uniquely given, but there's actually flexibility in what you can define to be the potentials. Like you could change these a bit. You guys have seen that in the homework problems where I've asked you to find either a function or a vector. Like some of the problems in the homework are like, find a vector field whose curl is a given vector field, right? Or there's other problems where I'm like, find a potential such that the gradient of the potential is equal to a vector field. Both of those kinds of problems, there's not a unique answer. Like for the potential, you can always add a constant, right? And for the curl problem, you can always add the gradient. Do you guys notice this? Like if I ask you guys to solve this thing, I say, okay, here's, you know, f, given f, find A such that f is equal to the curl of A, right? You got some problems like that in the homework, and if you guys ask me about them, I'd help you with them. But nobody ever asked me anything, so here we are. I'm being hyperbolic. I mean, you guys ask me questions on occasion. It's just the homework's not due soon enough, so you're not asking me questions about it. I should have made the homework due tomorrow. Then I'd had questions today. My bad. So this here does not have a unique answer, right? If you could find an A whose curl is f, check this out. If you take, if I put A2 equal to like the A which works plus like, you know, the gradient of any function g, well then what's the curl of A2? What's the curl of the gradient? It's 0. That's right. So you see, there's tremendous freedom in your choice of a so-called vector potential. In fact, so if you really look at it, in terms of the gauge freedom here, our freedom to choose potentials, you can add a gradient to the A and you can add a constant to the phi. There's actually apparently four independent things you can kind of tinker with. Well, that's not quite the right way to say it, but anyway. So see if I got anything else to tell you here. So again, that's the solution for the voltage. We just integrate the charge density divided by 4 pi epsilon naught difference between r and r prime. That integral defines a potential whose gradient is by construction the electric field, and minus the gradients of the electric field. Ah, come on! Double scrolling got me again. Seriously? All right, and then Ampere's law, on the other hand, if you start with Ampere's law here, so the Ampere's law this is with Maxwell's correction. I proved to you guys earlier in this semester that the presence of this implies the wave equation for the electric and magnetic fields through the tricky double derivative identities for curl and divergence. But anyway, so if I take the curl of this, B is the curl of A, so I just plug that in, substitute, right? But then you remember how the curl of the curl goes. It's the gradient of the divergence minus the divergence of this guy here, whatever that is. Oh, this is a funny formula, isn't it? But this is a vector equation, so it's a little funky. I'm trying to remember what this means. Divergence of the gradient. Oh yeah, but that's not right. I think this is something more. This is actually what this actually means is it's the Laplacian operator. That's nabla squared acting on A. So what that explicitly means. What that is like partial x squared plus partial y squared plus partial z squared acting on A. It's a vector of second derivatives of the components of A, which is why. And so if the divergence of A is 0, all right, then this just becomes the Laplacian on A equals to this business over here. And so that's essentially like a Poisson equation again, but there's 3 of them, one for each component of the vector potential. You get these 3 Poisson equations, each one of which you can solve in the same way we solved Gauss's, the problem for Gauss. And lo and behold, you get this formula. For example, for the first component of the vector potential, you just integrate the first component of the current density times mu naught over 4 pi. So anyway, there is a straightforward method for integrating the current density to get the vector potential, just like there is for the voltage. But, and there it is. So now, if you don't understand any of that, it's totally okay. I'm just sharing it with you for your future reference. If you ever are an electrical engineer or something, and you get to the point of your fields and waves course or something like that, you really should come back and think about this and try to connect the dots and make sure you understand how Calculus 3 meaningfully interacts with your study of flux, electric field, magnetic field, all those things. So, anyway. Oh, one other thing. You're like, I knew it was too good to be true. Right? So, my apologies. I keep forgetting to tell you guys about this. These are super nice. There is a formula for the divergence for the curl for the gradient in other coordinate systems. All right, so here's the formula for the divergence in spherical coordinates. So how does this help you? Well, check this out. If my vector field, for example, is, I don't know, let's say rho hat over rho squared, right? What's that? Remember this one? This is the xyz divided by, in Cartesian coordinates, this looks like, xyz divided by the square root of x squared plus y squared plus z squared to the 3rd power. This is the Coulomb field, all right? So if you're going to use these formulas, the first order of business is to understand the vector field that you're given in in terms of the spherical frame. So for example, this vector field, it only has a rho hat component, only a rho component, right? So what this would say is f rho is 1 over rho squared, f theta and f v is 0. All right? So to calculate the divergence of the Coulomb field, if you have this formula at the handy, right, you simply plug 1 over rho squared into here. This is 0. This is 0. So what's the divergence? What's the divergence? Well, so if I've got 1 over rho squared times rho squared, what's this? This is just 1, right? What's the derivative of 1? 0. So the divergence of this field is 0. Now, if you've already done that homework problem in Cartesian coordinates, you should appreciate how much easier this is. Right? Like a lot easier. Yeah.
But would we have to solve for that before doing it this way?
Well, I'm going to say that you can use, I will free you guys to use the divergence and the curl and the gradient formulas in non-Cartesian coordinates if you'd like, even though, sadly, I have not derived them in class. If you'd like to see the derivations, here they are. So like, well, we started doing this for, we started doing these derivations for like the gradient, right? We actually worked out the gradient in polar coordinates and cylindrical coordinates and spherical coordinates before. I think I have talked about this. But essentially, it's just like, there's two things going on. The one thing is you got to convert to write your vector field in the spherical basis, or the cylindrical basis in this case. And then you got to convert your derivatives to like r and theta derivatives. And it's a little bit of work, but it's just like straightforward. It's essentially just chain rule. Anyway, so like here's the divergence in cylindrical coordinates. It looks like this. It's a little bit surprising to me anyway that that's how it works, but there it is. That's how it works. If you have a problem with cylindrical symmetry and you want like an easy way to calculate the divergence, this might be a good choice. Sometimes, a lot of times, the divergence is just easier in Cartesian coordinates anyway. So I'm not saying you have to use these by any of the stretch of imagination. I'm just saying that they're useful to know about. Let me show you. So like here is a a summary, if you will, of this math. And these are not in my type notes because I don't know, I just haven't gotten to it yet. My bad, but so like the way this works is fx, fy, fz, these are your usual Cartesian coordinates for the vector field. You guys already know how to calculate the divergence and the curl in those terms, right? That was our definition. We started there. But again, if you apply the chain rule and do some vector algebra and convert over to the, so here, this is my notation for this before has been like r hat, theta hat, z hat, rho hat, phi hat, theta hat, okay? But the thing I got it out of uses the u, like it's a boldface u. Anyway, so here's the formulas for the gradient in cylindrical or spherical. Here's the formula for the divergence in cylindrical. The divergence in spherical is ugly. The curl, I think you can figure out how to use this formula, right? And here's how the curl goes in sphericals. And here's the Laplacian in cylindricals. Here's the Laplacian in sphericals. This will matter to you as an engineer if you ever take a course in quantum mechanics and, for example, you're trying to solve the hydrogen atom. The hydrogen atom has a spherical symmetry using spherical coordinates, makes Schrodinger's equation particularly beautiful, and at that point you'll need to know this in order to solve Schrodinger's equation wisely, which would be not in Cartesian coordinates. For example, there's an application of these formulas, but anyway. Listen guys, I will shut up. I just wanted to make you aware of this. I will send you guys, I'll put a link to this in Canvas so you know where it is, but it's in the archives.